Welcome. Today we look at the intermediate value theorem. A little bit underappreciated, but very beautiful. So we have a function which is continuous on some interval ab. And let's assume that the function is negative here at a and positive here at b. So this is assumption is that they just have different signs at a and b. And then the theorem is that there exists a root. A root is a place where the function is 0. So roots. So that's a place where f of x is equal to 0. So x is a root of f if f of x is equal to 0. So that's a root here. It's a very obvious result, right? If you go from here to here, you have at some point you have to cross that line. So the assumption is that f is continuous. And if the function is not continuous, of course, then it's wrong in general, right? We can have a thing like that we have the function is going here and then continuous here. So the proof of the theorem is actually much more than a proof. It's a whole method. It's a divide by and conquer method. So when you have the situation that you have an interval a, b, and the function is maybe negative here and then positive here, what you can do is you can divide the interval into two pieces. And then you look what happens with the function at that point c. So that's a plus b half. And if the function has different signs here and here, what you do is you continue with that interval and do the same argument than before. If it would be opposite, you would continue with that interval. So what happens is you have now a new interval which is half as big, and you have the same situation than before. So you have a function which is negative here and positive here. Maybe the next time when we do it again, and we will continue with the a2, b2. So that's now our new interval. In step n, we are the length, which is b minus a, times 2 to the minus n close to a root. It's a very important method, this divide by and conquer method. You do that also when you would have programming. You have a huge program, thousands and thousands of lines of code, and you want to know where the error is. There's an error somewhere, and the compiler doesn't tell you where the error is. You divide it by half. You just take half of the program, you see what happens there, and then if that's okay, you look at the other half. If it's not okay, if this is not okay, you continue with that and divide it up more and more. One of the applications of the intermediate value theorem is to make sure that equations have solutions. So if you have an equation, the left-hand side is equal to the right-hand side, like, for example, cosine x is equal to x, and we want to make sure that this has a solution, what we can do is we can reduce it to a root problem. So what we have is cosine x minus x is equal to 0. So here this is an equation, right? This is also an equation, but it's also a root problem. And now we can use the intermediate value theorem, or hope to use the intermediate value theorem. So why don't we take extreme cases here? So let's take f of maybe minus 1000 pi. So in this case, that's actually just 1. So this is equal to 1 minus 1000 pi. And if you take 1000 pi, you have also 1, but we have 1 plus 1000 pi. So if you look at this function, what happens is at minus 1000 pi and at 1000 pi, so we call this a, and this we call b. So what happens here in this case, we have something really negative, and we don't know how that looks like, and then we have something really positive here. So there's a solution to this equation. So it's actually something we can also visualize if you look at the graph of cosine x, which is here, and then you look at the graph of x, which is here. So cosine x and x, they have intersection somewhere. These graphs have an intersection somehow. But this is a root for this equation cosine x minus 6. So let's look at the following problem here. So we have a 100-meter race. So this is 100 meters. This is distance. This is 100 meters. And this is time here. Maybe this is 10 seconds. This is 5 seconds. And so on. 1, 2, 3, 4, 5, 6, 7, 8. So these are seconds. And this is distance. And so we have Achilles is a gentleman and gives the turtle advantage of 50 meters. So this is 50 meters. And they both have a speed. So Achilles actually, let's just assume Achilles runs with 10 seconds per 10 meters per second. So in average. So maybe Achilles does something. So he arrives here. And somehow like that, maybe a little bit slower than something like that. The turtle, however, so Achilles has a maybe 10 meters per second speed, and the turtle, they're actually very slow when they walk, 0.1 meter per second. And so what happens is that the turtle in 10 seconds has just gone 1 meter. So it actually kind of went from here to here. So we just make it orangey. We want to show that this actually, there's a place where Achilles was really overcoming the turtle. And so this is the place where the time when they were at the same place. And that's one of the Zeno paradoxes, is that this actually can never happen, because Zeno argued if Achilles reaches the 50 meters, the turtle has already gone further. If Achilles then continues to that place, then the turtle has gone even further. And so there are infinitely many times which are needed until Achilles reaches the turtle, so that they cannot really overcome the turtle. But here we kind of see the intermediate value theorem gives us a solution. And so how do we apply that? What we have to do is maybe we take the f of x is f of t is the Achilles position. So this is a of s. That's the turtle of s. Let me just call it a of s and turtle of, or let me just t. A of t, t of t. So this is a of t minus t of t. So at the beginning that's negative, right? Because the turtle has 50 meters ahead. So f of 0 is equal to minus 50 meters. And f of 10 seconds of 10 is actually this distance we know here. This is 49. This is 49 meters. So we see this function f has the property that it's negative here and it's positive here, and so this has switched sign. So there exists a root. By the way, a fun fact: if you would allow the turtle to swim, the turtle would actually be faster, or about the same speed. So there are turtles who actually swim as fast as a human can run. So that's the first application. Okay, let's assume this is the Earth and this is a point on the equator. This is the opposite point, polar point on the opposite side here. We claim when we have a temperature distribution, like T of x is the temperature at the point x. And we claim that there exists an x such a temperature at the point and at the opposite point is the same. We claim that there is a position so where t of x is equal to t of x plus pi. And what we do in order to prove this, to justify this, we define f of x is equal to the temperature at x minus the temperature at x plus pi. So what we notice is that f of 0 is just the opposite of f of, this is minus f of pi. So if you look at this function, this is kind of a nice function, which from 0 to pi, if you look at the graph of this function, we don't know anything about this function, but at 0, what happens is it's kind of, it's a negative, it has to be the negative thing. And the reason is if you put in 0, we get t0 minus t pi, while this here is t pi minus t2 pi, which is minus t0. So that's equal to t pi minus t of 2 pi, which is 0. So you see, that's just the opposite here. So this is the opposite of that. And so because it's the opposite thing, there has to be a point where f is equal to 0, and f is equal to 0 means just that we have a point where the temperature at the point and the temperature at the opposite point are the same. The wobbly table theorem is one of the famous applications of the intermediate value theorem. It tells you that if you are in a coffee shop on a table, on a square table, and the floor doesn't have to be even, and the table usually wiggles, right? Wobbles. So what happens is you can turn the table around, can also be a chair, so that all the 4 legs are on the ground. And it's a nice application of the intermediate value theorem. We will discuss this more in class, but what happens is you can look at the function of the 4th leg, the height of the 4th leg above ground, when 3 of the legs are on the ground. And what happens if you turn by 90 degrees, what happens is you can argue that the leg has gone underground. If it has been above the ground, it is underground. If it has been underground, it will be above the ground. And then by the intermediate value theorem, there has to be a place where all 4 legs are on the ground. So the last thing I want to do is already talk about maxima and minima. We will talk about this later. It's one of the major applications of calculus to find maxima and minima. But the local maximum is kind of something which is clear. So this is a maximum. It's like a mountain peak. It's a place where the function is maximal in a neighborhood. So what happens here with that interval around, this is the largest point. So this is called the local maximum, and we will assume for now only that the function is continuous. So it's continuous, not differentiable necessarily. We talk about differentiability next week. And let's just assume that h is a positive number, arbitrary, that's kind of like a step size. And then we say a is a h critical point if f of a plus h minus f of a is equal to 0. So here that would be a critical point in that sense, because at a and a plus h we are the same height. So we took that step h, like in snow, you are walking on snow, and you are here, you make one step, and you are at the same height, then that's what we call a h critical point. So we will also then, next week we start looking at derivatives, but we can define df is equal to, this is the, so we can define this is rise over run, and in this case, if that is equal to 0, that's equal to 0, that's equivalent, right? So what it means is that f8 a plus h, the height here, f a plus h is the same than f of a. So if a is a h critical point, there exists a local max or min on the interval a plus h. But it's actually false then in the classical setting. If you have a function like x to the 3, and you see when we take the derivative here, then we get 3x squared. That's 0 here, so it's flat, but it's not the maximum. It's not the local maximum or minimum. So here in this discrete setting, it's kind of more regular. Let me just tell you how you can reduce this to the intermediate value theorem. Okay, why is this true? This result here, it's an average rate of change, kind of from x to x plus h. It's the rise over the run here, but it's a discrete derivative, and that's equal to 0. That's our assumption that the initial point fx. So the assumption is that dfa is equal to 0, which means that the function value here and the function value here is the same. Now this will imply that there exists a maximum or minimum between. That's the result. And Bolzano was actually proving several theorems. Bolzano was also proving that there exists a maximum or minimum on a closed interval. But that's not constructive. What we actually have here is a constructive argument. We will actually construct a maximum or minimum. So it works like that. And this needs the intermediate value theorem. What we do is we take the midpoint. This is a plus h half. And so now we look at the value here. And we define a new function, g of x, which is f of x plus a h half minus f of x. So that's kind of something you have to think about. See it also geometrically, right? What you have is what you gain here, you lose here. So that's the same. What you gain here, you lose here. Now by the intermediate value theorem, so in this case, what we can do is we have a root. So we get by the theorem, we get the root. This tells us, kind of if you translate it back here, this tells us that we have found a point. So now we have found a point here, x, such that x plus h half and x, the function value here and the function value here is the same, but with a half of the distance. So now we have kind of found a new interval, but so this is a1 plus h over 2, such that the function now is the same here and here. So like that. Same. Now we can repeat that argument. So we have now just a smaller interval. We can repeat that and we find another place where the function value is the same here and here. And then another. And so it's a nested sequence of intervals. Each have half of the length of the one before. And so there will be a point then where we reach the extremum. So here you would do like that. You would find another where it's half of it, and you would find another where it's half of it, and so on. So you get to a maximum or to a minimum depending on the situation. But it needs the intermediate value theorem, and it is constructive, and it's both done by Bolzano.